Welcome the grade 12s. This is Mr. Ndabezita, and we are looking at physics electrical circuit. Now, this is what we have. Let me just try to zoom in. We have the following electrical circuit. So we have an electrical circuit like this. And we also have an internal resistance, and from there we have the resistors. We have 3 resistors that are connected in parallel, and these resistors they are connected to a 3 ohm resistor once again. Let me just do this. And we have an ammeter, which we can we have a switch here, which is a switch S, which is closed. We have a voltmeter reading that is connected here. Let me just do this. This is what we have. Okay, so we have a reading of 22.5 volts there, and we have an EMF of 24 volts. We have an internal resistance of 0.5 ohm. If that is visibly clear, I think it is. We have a resistor of 6 ohm. We don't know the value of R, but we have 18 ohm. And this is a 3 ohm resistor. So this is the circuitry that we have. We have an ammeter with a closed switch. EMF is 24 volts, internal resistance of 0.5. We are measuring the voltage, the external voltage of 22.5 there, because we have an internal resistance of 0.5. The total EMF of the source is 24 volts or 24 joules of energy that will be supplied to the circuitry, but there are some lost volts because we are reading 22.5 volts. So some of the voltages have been lost in order to overcome the internal resistance of the battery itself. Right. We have 3 resistors that are connected in parallel, 6R and 18 ohm. We have these parallel connected in series with that, and then we have the ammeter reading there. Just looking at this circuitry, we can see one of just a few things in here. This resistor will read the total current. Why? Because for an example, when the electron moves in this direction, we know that it will split into 3, and then they will come out as a 3 as well, and then they will combine here as 1. So the current that passes through the 3 ohm resistor would be the total current. This is very important for us to understand, as we can say, as we will see as we continue why. So that is fine. This is the external resistance of the source. We can calculate the internal resistance, and we can calculate some of the lost volts that were used. We call this the lost volts because this is the voltage that is not externally used, but this is the internal resistance in order to overcome the internal resistance of the battery. So we refer to this as the lost volts. Okay, so having explained the circuitry as it is, let's go and read what the information has for us. A battery with an internal resistance of 0.5 ohm and an EMF of 24 volts is connected to 4 resistors, a closed switch, and a high resistance voltmeter V with 22.3 volts and an ammeter of a negligible resistance as shown in the diagram on the board. the resistance of the connecting wires must be ignored, because if we take into consideration the resistance that is lost the resistance of the connecting wires, this is going to create such a very hectic problem for us. So we ignore the resistance of the wires themselves. We pretend as if there is no overcoming of any resistance as the electron travels through the wires, only taking into consideration the resistors that we have there. Right, be that as it may, we continue. In 9.1 they say, explain the term EMF of 24 volts. They want us to explain the EMF of 24 volts with reference to work done. So let me just write this down for you. 9.1, they want us to explain the term EMF of 24 volts with reference to work done. Right, I'm going to take you through Newton's classical mechanics, even though Lagrangian and the Hamilton view of classical mechanics would argue with Newton, but I will take you through that. So in answering this question, explain the term EMF of 24 volts with reference to work done. Now I know that work, according to classical mechanics, and we don't have to debate all that, work done would be, work is done when a force is applied and an object is displayed. Now, work is done when an electron is given power and it is able to traverse through the circuitry, then work would be done. So explain the term 24 volts EMF with reference to work done. So we can say 24 joules of energy supplied. This is 24 joules of energy supplied to do work. So we can say that's exactly what 24 volts would mean with reference to work done. So this would be 24 joules of energy supplied to do work on both internal and external circuit. Very, very important for us to understand this. So this is exactly what we are saying. We are saying that 24 joules of energy supplied to do work, because we have to do work first to overcome the internal resistance of the circuit and also the external resistance. So that 24 volts would be the energy supplied to do work on both internal and external circuit. I don't know how your teacher would explain this, but this is just a net summary of exactly what work would mean with reference to that 24 volts, because I know that 24 volts is the maximum energy of the external and internal circuit. Right. And then in 9.2 they say to us, calculate the current in the 3 ohm resistor. 9.2.1 they want the current. They want current in the 3 ohm resistor. So we want to know how much of current is flowing through the 3 ohm resistor. Remember what we said previously. We said that total current flows in the 3 ohm resistor. Now we have a problem here. If I try to find the current on the 3 ohm resistor and I don't have the voltage in that 3 ohm resistor, I'm having a problem. I don't have the current, I don't have the voltage, I can find this. If I try to find the voltage of the V parallel, somebody might say I don't have R, this is the problem. But there are some other external ways of finding the voltage across the parallel without even having that. So how will I go about solving this? Now my approach would be the following. I know that EMF is equals to the total current multiplied by the external resistance plus the internal resistance. This is the total resistance of the circuit as a whole, including the resistance inside of the battery, where this IR. If you use the distribution law, you will get IR here. What is this? This is the voltage, because current multiplied by the resistance will give you the voltage based on Ohm's law. So this would be the voltage of the external circuit. This is the total resistance of the external. This is the total resistance of the internal. So this would be external voltage, and this would be internal voltage. Okay, so is that going to help me in anything? Yes. I think that I have the EMF, okay, and I have the internal resistance. I can find the current there. I can say that, okay, EMF equals IR, and I'm calculating what here? I am calculating the lost volt, the voltage that is lost as we are trying to overcome the 0.5 ohm resistance. Do I have the EMF? Yes, that's 24. Do I have, remember, inside of the battery, total current is flowing there. Very important. Do I have the current? No, I know this is the total current because total current flows inside of the battery. And then I multiply by the internal resistance. Do I have it? Of course, it's 0.5. And then I want to find the total current. I can just divide by a 0.5 and a 0.5, and I will find the total current as follows. So let me just go to the calculator very quickly and see what I would have. So I will say 24 divided by 0.5. And I find this is 24 divided by 0.5. Let me check this. EMF is 24. I'm looking for total current, and I multiply this by 0.5 of resistance, and I find a value of 48. No. I cannot approach it in this way. I'm having very serious problems with this, because this would give you 48 amperes. This is totally out. So you wouldn't go for this. Now let me show you what to do since this doesn't work. Let me show you what to do here. What I will say is the following. I am given the voltage of the external circuit, which is 22.5 volts. Very important. So what I can do, I can say, okay, I know that EMF equals IR. And what is this? This is the voltage of the external circuit. What is the voltage of the external circuit? So here you cannot say E, you have to say V external. The external voltage of this, because this is total current, multiplied by the total resistance of the external circuit. So this would be the voltage of the external circuit, which is 22.5. I know that in the external circuit, not taking into consideration whether this is parallel or series, but a combination of both, that should give you the total current. So this is IT multiplied. Do you have the resistance of the external circuit? No, you don't have it. So this is highly problematic. I cannot find the value of R. So this would fail because I have two unknowns. Okay, so where do I go from here? All right, now the second approach would be to calculate the lost volts. I know that EMF equals I into R plus R, where this is IR plus IR, and this is your EMF. Okay, now what is the value of the EMF? It's 24. What is the voltage of the external circuit? It's 22.5. The voltage, current multiplied by the resistance, is the voltage but of the external circuit, which is 22.5. Now I can find the voltage of the internal V internal, the lost volts, the voltage that was lost trying to overcome a resistance of 0.5. And I can say that IR equals 24 minus 22.5, and your IR would be as follows. So I can say 24 minus 22.5, and I would find the lost volt as 1.5 volts. What is this? This is a V internal. I now have the voltage of the internal circuit. I know that inside of the battery the total current flows in there, so I can say that V internal equals I total multiplied by the resistance of the internal there. I have V internal, the voltage that was used to overcome the resistance of the battery, which we call the lost volt. Yes, that's 1.5. I'm looking for total current because I know inside of the battery total current flows. Do I have the value of R, the internal resistance? Yes, that's 0.5. And I can divide by 0.5, 0.5, and now I can find the total current. And that would be 1.5. Divide that by 0.5. And I find a value of 3 amperes. What is this? This is the total current. And I know inside of the 3 ohm resistor total current flows. So that is to say, current across the 3 ohm resistor equals the total current, which is equals to 3 amperes. And you are done. You are completely done. So I know it might have taken some time. I just wanted to show you the different approaches and where you could go wrong with this. And finally, the correct way of looking at that. Because in these lectures of Mageba Mlotshwa himself, we're not just here to just go straight and then you are trying to copy from the memorandum and pretending to understand. No, we are doing things thoroughly so that whoever is watching can see that the guy knows exactly what he is talking about. Very good. Now let's go and try to do 9.2.2. And then the question that we have, it says calculate the power that is dissipated in the 18 ohm resistor. So how much of power is being used in 18 ohm resistor? That's what we want. We want to find the power in the 18 ohm resistor. So we want the power in the 18 ohm resistor. I know that power is equals to I squared R, or power is voltage in the 18 ohm resistor multiplied by the resistance, multiplied by the current that is flowing in the 18 ohm resistor. So two formulas can be used and they should give exactly precise the same answer for this. Now, how do we calculate the power that is dissipated in the 18 ohm resistor? First of all, I will have to look that these 3 resistors are connected in parallel, and I know that in a parallel circuit, the total voltage is the same, but current divides. That's exactly what I have tried to explain. So how about I calculate the voltage in the parallel combination? So I would say, okay, V parallel, I know that in the parallel circuitry, if I combined all those currents, they must give me the total current. So meaning, in a parallel circuitry, total current flows. So this would be the total current multiplied by the resistance of the parallel. But this would not work since I don't have R parallel. Okay, is there any other approach? I think I can do so. I think there is. I can calculate the voltage that flows in the 3 ohm resistor, and that voltage I would subtract it from 22.5 and I will know the voltage in the parallel combination. Clever way of looking at this. So the first thing, let me just try to find the voltage that flows in the 3 ohm resistor. That will be the total current because that's what the current is flowing in the 3 ohm resistor, or you can say and the current in the 3 ohm resistor multiplied by the resistance of the 3 ohm resistor. We have current as 3 amperes. I multiply this by the resistance, which is 3, and I get 9 volts. This is the voltage that is being used in the 3 ohm resistor, the amount of energy that it's required for that. Looking at 9.1 hours as our reference, explaining that 24 volts would be 24 joules of energy supplied to do work. So we require 9 joules of energy to do work in that 3 ohm resistor in that sense. Now that I have the voltage in here, I can find the voltage of the parallel, where I say V parallel equals V external minus the voltage across the 3 ohm resistor, because this is the only combination that I have. So I would say V external is 22.5, I would minus 9, and I should get a value there. 22.5 subtract 9, and I only have 13.5 volts. So this is the voltage that is being used for the parallel combination, knowing that in a parallel combination voltage is the same. Now that I have the voltage in here is the same as in here and there, now I can find the power dissipated in the 18 ohm resistor. And I can say, okay, this would be, I'm not going to use, which one? Let me check. I don't have the current that is flowing in the 18 ohm resistor. I have a problem. Even if I use this is also problematic because I don't have the current in the 18 ohm resistor. So I think that is what I should try to find first. I can find the current in the 18 ohm resistor. Why? Because I have the resistance and even the voltage there. So I can say, okay, the current in the 18 ohm resistor equals the voltage in the 18 ohm resistor divided by the resistance of the 18 ohm resistor. The voltage is the same. I just calculated the voltage as 13.5 divided by 18. And let's see, remember why I have this. I have used Ohm's law. VIR. Voltage, current is voltage divided by the resistance. And let's see exactly what we will have from this. So I'm having my 13.5 and I am dividing this by 18. And I'm getting 0.75 amps inside of the 18 ohm resistor. Now I can find the power now. I can even go for this one. So power would be the current that is squared. Remember what I'm calculating here. Let me just specify. Power in the 18 ohm resistor equals the current in the 18 ohm resistor, that is squared multiplied by the resistance of the 18 ohm resistor. And I would find the value as 0.75, that is squared multiplied by the resistance, which is 18. And let's see what value we would find. So I have my 0.75, that is squared multiplied by the resistance of 18, and I find a value of 10.125. 10.125 watts. This is the power, because power is measured in watts. So I take the current, I square, I multiply it by the resistance. What if I use the formula? Power in the 18 ohm resistor equals voltage in the 18 ohm resistor multiplied by the current in the 18 ohm resistor, because that's also how you calculate your power. So the voltage in the 18 ohm resistor, I know that voltage is the same. That's 13.5 multiplied by the current, which is 0.75, and we should get exactly the same value there. But let's try to verify that. 13.5, and this would be multiplied by 0.75, and we get a value of 10.125 watts. That's exactly what we find there. And having found that, we can continue in this. We can continue in this. We can continue in this. Now, let's try to look at something. Let me just go and look at the formulas that are provided for us, so that I don't make any mistakes when it comes to this. Power is voltage times the current. That's true. Power can also be equals to I squared R. That's very true. Or power could be V squared divided by R. It doesn't really matter, but this is exactly what we find. Okay, that's fine. Let us continue in this. Right, and then from there, I want us to calculate the following. They say to us, we should find the value of resistor R. Current in resistor R in 9.2.3. 9.2.3. They want the current in resistor R. They want current in resistor R. This one. Already a lot, I think I understand this. I know the voltage across the resistor R, and I'm looking for the current. I don't even have the value of resistor R, but that's fine. That's very fine. What I can do is to find first, let's try and find the current that passes through the 6 ohm resistor. Let's try to find the current that passes through the 6 ohm resistor. Why would I do that? I have a very serious problem with R. I don't have the value of R. I don't have the current that flows in R. So I'm going to have some very serious problem even if I can find the current that is flowing in here. I don't have the resistance value of R. So let me find the current that flows through the 6 ohm resistor. So current in the 6 ohm resistor equals voltage in the 6 ohm resistor divided by the resistance of the 6 ohm resistor. Now the voltage is in the 6 ohm resistor. I know that the voltage is 13.5, and I will divide this by the resistance of the 6 ohm resistor, which is 6, and I can find the value there, and I can say 13.5 divided by 6, and I will find 2.25 amperes. And this makes a lot of sense because I know if your resistance is smaller, more current will flow when we contrast the two. You have a higher resistance, smaller current flows. You have a lower resistance, more current flows. So now I can know the current that flows in resistor R by saying the current in resistor R equals total current. Let me do this. Let me say IT minus current in the 18 ohm minus current in the 6 ohm resistor. I total, it's 3 amperes. I will minus 0.75, and also minus 2.25. Whatever that is left will be the current that flows in resistor R. So I can say 3 minus 0.75 minus 2.25. And I will find a value of 0. Jesus! Is this true? Guys, please help me with this. Please help me a lot with this. It says that the current that is flowing in this resistor would be nothing. You mean to tell me that 2.25 plus 0.75 would give you 3. Is this true? Let's check. 2.25 plus 0.75. Yes, we get 3. Oh, we are having a serious problem here. This is a very, very serious problem. I never and ever anticipated this coming. The current in the 6 ohm resistor, the voltage is the same as 13.5. I divide this by the resistance of the 6 ohm resistor and I get 2.25. Okay. So you mean to tell me that the current that flows in that, there's no current there? Unfortunately, that's what we have. 0 amperes. That's 0. This is unfortunate. This is highly unfortunate. To be honest, this is so unfortunate. There's nothing that we can do. 2.25 plus 0.75 will give you 3, and then 3 minus this, so there's no current that is flowing in the 3 ohm resistor. Unfortunately, this is the case. Nothing is wrong that we have done. This is just a fact of a calculation. So there's nothing that I can do. I am as flabbergasted as you are right now. But this is the fact of the matter. There's nothing that we can do. Now let's continue with the questions. The laptop is freezing. I think it's also surprised with the results that we have on the screen. But this is exactly what we have. Okay, I don't know what the next problem would be. The computer just froze. Let me just wait for it to recover before we can go any further. Now, it says in 9.3, resistor R is now removed from the circuit. So let's try to remove it. Because it contributes 0, no current is flowing from this resistor. This is what we have if we remove resistor R. Will the power dissipated in the 18 ohm resistor increase, decrease, or remain the same? Explain. Will the power dissipated in the 18 ohm resistor increase, decrease, or remain the same? Now let's look into this. The power dissipated in the 18 ohm resistor was 10.125 watts. Okay? Because voltage was the same. And if we remove that resistor, V parallel is not going to change. If we remove that, even if we increase those resistors, V parallel will remain the same. Okay? We will still have the 9 volts. So the method of calculating power, which is V times I, if voltage remains the same, the current that flows in the 18 ohm resistor would also remain the same because of the value of R. So what would happen then? So let's say the following. Before we can say increase, decrease, or remain the same, let's just first say V parallel remain constant, or it remains the same. Let's say it remains the same, because the same and constant are two different things. By removing that, because there is no current, as we saw, that is flowing on the resistor R, so it's just there as a resistor with I don't know, but there's no current that is flowing. It's like it is not even there. It's like it's not even there. So V parallel will remain the same, because whether it is there or whether it is not there, it doesn't make any difference. V parallel remains the same. So if V parallel remains the same, so meaning the power in the 18 ohm resistor will remain the same. So power across the 18 ohm resistor remain the same. Meaning again current flowing in the 18 ohm resistor remain the same. These are the three things that we can say. V parallel remains the same, the power in the 18 ohm resistor remains the same, because of the current flowing in the 18 ohm resistor remains the same. Whether you have R or whether you don't have it, it doesn't make any difference, because there is no current that is flowing in there. Very, very important. There are no lost volts in there, because there is no current flowing. There is no resistance. In other words, there's nothing there. It's just placed there as an obstruction to us. That has nothing to obstruct. It obstructs nothing. It prevents nothing. It causes a barrier on nothing. Nothing of a change it does in the circuit. So these effects remain the same. And this is just something that I wanted to share with you, the grade 12s. And I will see you in another tutorial.